Comparative study of pre-engineered building and conventional steel building. Abstract pre-engineered building, PEB, concept is a new conception of single-story industrial building construction. This methodology is versatile not only due to its quality pre-designing and prefabrication, but also due to its lightweight and economical construction. The concept includes the technique of providing the best possible section according to the optimum requirement. This concept has many advantages over the conventional steel building, CSB, concept of buildings with roof truss. This paper mainly focuses on PEB concept and CSB concept and how we can choose the concepts for practical application. The study is achieved by designing a warehouse building as PEB and as CSB with the help of Staad Pro. Keywords: pre-engineered building, conventional steel building, tapered sections, wind load, Staad Pro. Introduction. Steel concrete composite structures are gaining significant importance all over the world in the recent past. Steel concrete composite construction technique offers number of advantages like increased load carrying capacity and stiffness, saving in weight of steel, reduction in cost of foundation and most importantly a large saving in construction time. Composite construction also leads to a reduction in the overall weight of the structure, which is a prerequisite for earthquake-resistant structures. With the increased demand on strength, safety, and reliability in all types of structural systems, it has become imperative for developing countries like India to adopt steel concrete composite construction technique in large scale. A conventional steel building, CSB. Conventional steel buildings, CSB, are low-rise steel structures with roofing systems of truss with roof coverings. Various types of roof trusses can be used for these structures depending upon the pitch of the truss. For large pitch, Fink-type truss can be used. For medium pitch, Pratt-type truss can be used and for small pitch, Howe-type truss can be used. Skylight can be provided for day lighting and for more day lighting, quadrangular-type truss can be used. The selection criterion of roof truss also includes the slope of the roof, fabrication and transportation methods, aesthetics, climatic conditions, etc. Several compound and combination type of economical roof trusses can also be selected depending upon the utility. Standard hot-rolled sections are usually used for the truss elements along with gusset plates. B. Pre-engineered building, PEB. Technological improvement over the year has contributed immensely to the enhancement in quality of life through various new products and services. One such revolution is pre-engineered building, PEB. PEB means a part of fabrication, cutting and welding is completed at factory, then it just delivers and erects at the site without doing any fabrication work. Pre-engineered steel buildings are manufactured by companies such as IETC, Mabani Steel, Interarch Buildings Product Ltd, EPS Buildings, and PEB Steel. PEB systems are extensively used in industrial and much other non-residential construction worldwide. This concept was introduced to the Indian markets in the late 1990s with the opening up of the economy and a number of multinationals setting up their project. Various analysts forecast the pre-engineered building, PEB, market in India to grow at a CAGR of 16.15% during the period 2016-2024. Pre-engineered steel building can be fitted with different structural accessories including mezzanine floors, canopies, fascias, interior partitions etc. and the building is made waterproof by use of special mastic beads, filler strips, and trims. This is a very versatile building system, and can be finished internally to serve any functions and accessories externally to achieve attractive and unique designing styles. It is very advantageous over the conventional buildings and is really helpful in the low-rise building design. PEB are generally low-rise building. However, the maximum eave height goes up to 25 to 30 m. The applications of PEB concept to low-rise buildings are very economical and speedy. Buildings can be constructed in less than half the normal time, especially when completed with the other engineered subsystems. See applications. Pre-engineered building concept have wide applications including warehouses, factories, offices, workshops, gas stations, showrooms, vehicle parking sheds, aircraft hangars, metro stations, schools, recreational buildings, indoor stadium roofs, outdoor stadium canopies, railway platform shelters, bridges, auditoriums, etc. PEB structures can also be designed as relocatable structures. Conventional steel building applications include multi-story buildings, heavy-loaded industrial facilities, or special shapes for architectural features, etc. The objective of the study: to design a warehouse building for food products, 24m x 48m, as Type I, pre-engineered building, PEB. Type II, conventional steel building, CSB. Comparative study of PEB and CSB in terms of quantity of materials, axial forces, and moments. 2. Methodology. Present study focuses on the concept of pre-engineered buildings and conventional steel buildings. A warehouse for the manufacturing and storage of food products is considered and designed as PEB and as CSB, designated as Type I and Type II. Type I is pre-engineered steel building of length 48m and span 24m. Bay lengths are maintained at an interval of 6m along the length. The eave height of building is taken as 7.8m. The slope of roof is taken as 11 degree and covered with roofing sheet. The spacing of purlins is maintained as 1.42m. Type II is conventional steel building of length 48m and span 24m. Bay lengths are maintained at an interval of 6m along the length. The eave height of building is taken as 7.8m. The slope of roof is taken as 11 degree and covered with roofing sheet. The spacing of purlins is maintained as 1.42m. A. Functional requirements. The functional requirements of the proposed warehouse are: size of warehouse, 24m x 48m. Slope of the roof, 11 degrees. Single bay length, 6m. Eave height, 7.8m. Is 2062 material with a minimum yield strength of 340 N/mm2 will be used for main frames of PEB. GIZ purlins of minimum 3.2 mm thick will be used as purlins and girts. Bare galvalium sheets 0.63 mm thick, trough shape, will be used as roofing sheets. 0.63 mm thick pre-painted galvalium sheets, PPGA, will be used for side and cladding. Walls will be 3m high and 0.20 m thick laterite masonry in cement mortar of 1:3 and finished with cement concrete coping of 50 mm thick. Masonry will be supported on plinth beams spanning between the pedestals. Foundation will be based on the SBC of soil and the expected pull-out force due to wind. In this case, isolated footing. B. Loads. 1. Dead load, DL. Dead loads include the weight of all permanent construction. For example, in a building, weight of roofs, floors, floor finishes, wall, beams, column, footing, architectural finishing materials, etc. constitute dead load. These loads may be assessed by estimating the quantity of each material and then multiplying it with unit weight as per IS 875, Part 1 1987. 2. Live load, LL. /impose load, IL. The loads which keep on changing from time to time are called live loads. Common examples of such loads in a building are the weight of the person, weight of movable partition, dust loads, and weight of furniture. These loads are to be suitably assumed by the designer. It is one of the major loads in the design. The minimum values to be assumed are given in IS 875, Part 2 1987. It depends upon the intended use of the building. 3. Wind load, WL. The force exerted by the horizontal component of wind is to be considered in the design of buildings, towers, etc. The wind force depends upon the velocity of wind, shape, size and location of buildings. A complete detail of calculating wind loads on structure is given in IS 875, Part 3 2015. Brief idea is given below. Using color code, the basic wind velocity VB is shown in a map of India. Designer can pick up the value of VB depending upon the location of the structure. To get the design wind velocity VZ, the following expression shall be used. Where K1 equals risk coefficient. K2 equals coefficient based on terrain, height, and structure size. K3 equals topography factor. K4 equals importance factor for cyclonic regions. The design wind pressure is given by PD equals design wind pressure. PZ equals wind pressure at height Z. KD equals wind directionality factor. Ka equals area averaging factor. Kc equals combination factor. Wind loading on individual structural members such as roofs, walls, and individual cladding units and their fittings as per IS 875, Part 3 2015. F equals CPE CPI, *APDEQ, 4. Where CPE equals external pressure coefficient. CPI equals internal pressure coefficient. A equals surface area of structural element or cladding unit. See load calculations. 1. Dead load for type 1. As per IS 875, Part 1 1987, item number 39, Class A for 0.63 mm thick metal sheeting the maximum load is equal to 0.056 kN/m2. Weight on frame due to roofing sheet equals 0.336 kN/m. As per IS 875, Part I 1987, Table 1, item number 49, for unbounded rock and slag wool the maximum load between 11.30 kN/m3 to 19.60 kN/m3. For 25 mm per length of sheet take 15 kN/m3. For results and discussion. The weights of conventional steel building and pre-engineered building are calculated after the design. For conventional steel building the weight of the section is given in Table 3 and that for pre-engineered building is given in Table 4. A weight of the steel for conventional steel building. In order to calculate the steel weight of conventional steel building the following member properties are used. Table 3. Hot rolled I sections are assigned for columns. For the truss members Indian standard angles are used. For purlins, girts and eave strut ISMC, Indian standard medium channels, are used. Now using the above parameters the weights are calculated accordingly. B. Weight of steel for pre-engineered building. In order to calculate steel weight of PEB the following member properties are used. Table 4. For columns and rafters tapered I sections are assigned. For the purlins and girts cold formed Z sections are used. See comparison of axial forces and moments. Comparison of member forces and joint displacements at ridge and haunch portion with critical load and at same location was as mentioned below. From the comparison it is observed that at ridge and haunch of the building maximum bending moment for PEB is more than CSB by 4.81% and 16% respectively. This is due to the entire force will concentrated in PEB whereas in CSB it is distributed. At ridge of the building axial force for CSB is more than PEB by 18.31%, at haunch of the building PEB is more than CSB by 27%. This is due to the entire force has to transfer at haunch like beam action in PEB whereas in CSB it is like a truss arrangement. At ridge and haunch of the building shear force for PEB is more than CSB by 16.5% and 30%. This is due to the entire force will concentrated in PEB whereas in CSB it is distributed. V. Conclusions. Choosing steel to design a pre-engineered steel structures building is to choose a material which offers low cost, strength, durability, design flexibility, adaptability, and recyclability. In light of the study, it can be concluded that PEB structures are more advantageous than CSB structures in terms of quality control, speed in construction, and simplicity in erect. The total steel takeoff for PEB is 45% lesser than that of CSB. It is observed that maximum moment will be high for PEB than CSB. The axial force at ridge is higher for CSB than PEB, but axial force at haunch is higher for PEB than CSB. The shear force for PEB is greater compared to CSB. Architectural versatility. But we cannot completely conclude pre-engineered building should be used for all constructions. Because the concept of PEBs introduced from the conventional methods and there are cases where we cannot adopt PEBs such as projects which lacks funds for the high initial investments. For small span structures. Places far from the PEB manufacturing factories and CSB materials are locally available, etc. Hence it can be concluded that both the concepts are useful for the future construction industry with improved versions and design criteria. Steel building find a large scope for the future of Indian construction industry, and the day is quite close when steel buildings would be the rule rather than being the exception.